typically taught that any problem can be solved if we just try hard enough and think long enough. Does this hold true for programming? In this lesson, we'll learn about which problems can and cannot be solved, and how to evaluate and discuss an algorithm's efficiency and effectiveness. Hold on tight, it's going to get a little theoretical. You are probably not surprised at this point to find out that the answer to the question, can computers solve every problem, is no, absolutely not. It might surprise you to find out that someone has actually proven that computers cannot solve every problem. Until now, we have been talking about problem solving with computers and computational thinking in terms of algorithms. And an algorithm is the way to get the correct answer, the way to solve the problem. Of course, it's just a matter of finding the specific steps that you need to use and using sequence selection and repetition to get them to run the way you need. The question is, what about problems that we do not even know how to solve? Problems that no known algorithm can sufficiently address. And then what about problems that can be solved, but we just don't have the resources or the information needed? So although some problems cannot be solved efficiently through computation, or in some cases, as we'll talk about, they can't be solved at all, a lot of times there is a method for getting the closest we can get to a solution, even if it's not the exact. And this is known as using heuristics. Heuristics are a problem solver's kind of rule of thumb. They serve as a general guideline meant to encourage progress toward a good answer, but not necessarily guaranteeing that you are going to come up with the perfect correct answer. Another problem like this is known as the traveling salesman problem, where we find that it's actually surprisingly difficult to plan a route for a salesman who needs to visit, say, 10 different cities and needs to choose the most efficient path. So you would assume, well, I'm just going to start by going to the city that's the closest and then traveling to the next city that's closest to that one. However, you might find that your path is actually longer than if you would have maybe gone to a city farther away at first and then gone to another city that was further away, but then eventually maybe the path would have been shorter. So again, it's a heuristic. You can't find really the best solution. It's unreasonable, the amount of time it would take to find the best solution. So you just do the best that you can. You might be familiar with the name Alan Turing if you've ever seen the movie The Imitation Game. In fact, he is one of the most influential figures in computer science. He had a lot to do with the development of the digital computer. Prior to his work, computers were actually mechanical, and they were really more calculators than computers. But he had a lot to do with bringing us into the digital age. And he actually took the time to prove that at least one task is computationally undecidable, and that is known as the halting problem. So the halting problem, in that, he proved that you cannot write a program that will tell you which computer programs will halt, meaning exit or stop running, and which ones will continue running forever. So if you remember, we talked about iteration a lot, so a forever loop, and stuck in that loop with no way of possibly getting out. And so for whatever reason, I'm sure he had a great reason for this, he really spent a lot of time to prove that you can't write a program that will tell you which computer programs will halt and which will continue forever. And so that's a pretty interesting thing to investigate further if you're interested. But fortunately for us, most computer scientists spend their time constructing programs for problems that can be solved. And even so, there are often many different approaches to solving the same problem. There are multiple ways that a problem can be solved, and sometimes one is better than the other, and sometimes it just doesn't matter as long as the problem is solved. So how do we know when one algorithmic solution is better than another? In order to answer that question, we're going to have a way to evaluate the performance and then compare it to others. The first criteria that we can use to evaluate an algorithm is scalability. So how well does the algorithm perform as the size increases? So picture kind of a low quality graphic that you're trying to put into a presentation or a web page or something like that. And as you increase the size of the picture, it becomes pixelated. So as the size of the picture increases, the quality of the picture decreases. So thinking in computer science terms, if we have a list of who knows what, a list of students, a list of grades, a list of books that are in the library, and we double the number of items in the list, how much harder does it become to find one of those items, to target in on one? And then by the same token, what if we then triple the size of the list and quadruple it? And what if we increase it by an overall factor of n, some unknown number? But we can assume that n is really, really big. So how much does that increase the amount of work that is required by the algorithm, and also the amount of time that it's going to take to run? Computer scientists use something called the big O notation. We're not going to really worry about all of that math here. As a matter of fact, there are some concepts that we'll talk about, for example, logarithms, quadratic functions. And if you are not there yet, don't worry about it. You don't really need to understand the math behind it. But you do need to recognize the graphs and understand how they can help us evaluate algorithms. So first of all, we've got a constant relationship. And notice that the x-axis down here is the size of the problem, in other words, the size of the list, or how many items are in the list, or how many calculations have to be made. And then, of course, over here on the y-axis is the amount of work. All right, so we can see that in a constant relationship, as the size of the problem increases, it still takes the same amount of work to calculate it. Okay, so we can assume that values are not getting really large, or it's a constant relationship. So there's a straight line showing that as the size of the problem increases, the amount of work stays more or less the same. All right, then we'll move over here to the logarithmic notation. And this relationship here shows that every time you double the size of the problem, one extra unit of work is required. So looking at the graph here, we can see that when the size of the problem is very, very small, there's almost no work required. We're at the 0, 0 point. However, as the size of the problem grows bigger, the amount of work does increase, but not a whole lot, not in any really unmanageable or unpredictable way. So that logarithmic relationship means that it's a relatively scalable solution. All right, moving on to the linear relationship. Here we have almost a straight line coming up with a constant slope. And so we can see that the size of the pattern down here, as it increases, the amount of work, again, does increase. And it increases, as a matter of fact, at about the same rate as the size of the problem. So you can almost predict with this relationship here that, yeah, when you have a really big problem or a really huge list, it's going to be a decent amount of work, but probably doable. And we can probably predict the exact amount of time that it would take. Again, relatively scalable. And finally, we come over to the quadratic relationship. All right, you may have heard of the quadratic equation, you may have seen a graph of a quadratic function, but essentially, if you haven't, don't worry about it. You can see the shape of this line is a curve. All right, and the slope of the line starts off at a fairly steady rate, but then starts to increase fairly sharply. And really, once you get here, the line is going almost straight up, right? So what we can see is that as the size of the problem grows, the amount of extra work required actually increases, and it increases fairly quickly, and eventually is going to reach a place where the amount of work is too much, and it's going to reach that fairly quickly. And so this is actually not a very scalable solution. All right, so on the exam, I don't believe that you're going to be asked to talk about logarithmic or quadratic functions, but you do want to be able to recognize these graphs. And you want to know that the one to be on the lookout for is this one over here, which is the one that shows that once you hit that upward direction of the arrow, you are not scalable anymore. So to conclude, you can basically evaluate the scalability of your algorithm based on these graphs. And the graphs are in order of scalability. All right, so constant is the most scalable relationship. Logarithmic is next, not quite as scalable. The work is going to increase, but not that much. Linear is less scalable, although still scalable, just depending on knowing how large can this problem get. So maybe if we know the problem is going to be really extremely large, we wouldn't want to use this one. And then of course over here, this is the least scalable of the four. So now let's go take a look at a search comparison where we're going to look at two different algorithms for searching through a list. And we're going to see if we can get an idea of whether we can evaluate if one of the methods is better than the other. All right, let's take a look at this little simulator. This simulator allows us to think of a number between 1 through 1,000, and note the use of the word inclusive there. That means that yes, you can include the number 1 and the number 1,000. Based on either using a sequential search or a binary search, this program is going to guess our number with the not so supercomputer smarts or with the supercomputer smarts. All right, and here it says that with sequential search that it guarantees to us that it can perform this search in 1,000 guesses or less, because remember, we're allowed to choose up to the number 1,000. And over here, the claim is that it will guess our number in 10 guesses or less. Very interesting. I will share the magic number that I'm thinking of. I am thinking of the number 56. All right, so I am going to go over here to the sequential search, and of course the first guess is 1. All right, they've already put that there. That was there when I opened this web page. So that is not correct. Okay, well, how about 2? Nope, not correct. My number was 56. How about 3? Nope, not correct. All right, hopefully you can see where this is going. I am going to have to click, click, click through this list up to the number 56 to get this program 56. That is correct. Aw, yeah. All right, but that wasn't really very efficient in that particular situation. If this was a matter of time and I had to sit and hit the button 56 times to get the correct answer, that wasn't that great. All right, let's set that up again. Over here, we have binary search. So remember, what's happening here is, well, I don't know if you remember or not. I don't think we've talked about it. In binary search, we are actually eliminating half of the list right off the bat. And that's why this program guesses or tells us that it's going to guess our number in 10 guesses or less. All right, so they guessed 500. Well, if we stick with the number 56, we have to tell them that is too high. All right, interesting. Now the guess was 250. All right, so it was 500. Now it's 250. Well, that's still too high. Can you predict what the next guess is going to be? 125, were you right? Well, that is still too high, so I'm just going to keep hitting the too high button, but I've only hit the button 4 times so far. Ooh, it is still too high. 6 guesses remaining. Aha! And now it went to 31, okay? And there's 5 guesses remaining. That number was too low. The next guess was 46. Very interesting. All right, so there are 4 guesses remaining. That one is too low. 54 is too low, but not by much. 58 is too high. 56. There we go. All right, so you can see that it cut half of the possibilities every guess. So the first guess, it found out whether my number was in the top 500 or after 500. With the next guess, it found whether it was within 250. Then it went to 125. So it kept cutting the list in half. And so you can see that that was a much more efficient way to find my number. So it would seem like our binary search would be the way to go. It's more efficient. It took less guesses. Well, I will tell you that the fact that we used numbers, that it was guessing a number, even if it was guessing a letter, numbers are in order. Just like letters can be in order. There is an order to numbers. And the list that is being searched in this particular example is absolutely in order. If our list were not in order, if this was a randomly sorted list, like for example, a list of things that people had entered in on a grocery app or something like that, if those things are not sorted, binary search will not work. So that would be unfortunate. We cannot use binary search if our list is not already in order. Now, of course, we can put it in order first and then search it, but at that point, are you making more work for yourself than just using sequential search, right? So you have to think about these things and think about, the type of data that you're searching and sorting and the amount of time that you have. And if it's easier to sort and then use binary search, great. Otherwise, if it's easier to just use the sequential search and know that it's going to work every time, great. So imagine if you needed to search through a list of 1 million items. If the item were one of the first few items in the list, then sequential search would be great, and it would be very precise, and it would work every single time. However, as the list grows longer, and if your item is at the end of the list, sequential search, in worst case scenario for this particular problem, would need to look as many as 1 million times. And so on average, depending on where the item might be located in the list, sequential search will require you to go through about 500,000 items. Assuming that it's somewhere before or after halfway through. So this is referred to as having a linear performance because there's a linear relationship between the size of the problem and the amount of work required to solve it. Compare that to binary search. It does not have that same one-to-one relationship between the size of the problem and the amount of work. Because what it does, the term binary, hopefully, is a little bit of a cue for you that this is something to do with two different possibilities, right? We said binary was kind of the same as true or false. And so in this particular case, we have, in the example that we used, you saw it asks if your number is greater than what it guessed or less than what it guessed. And those are two possibilities. It's either that or the other because we know it's not right because you told it was wrong, right? So it branches it off into two branches, knowing that it can only go one way, or it only has to go one way. So even at the first guess, it has eliminated half of the list. So with this logarithmic behavior, you can actually double the number of items in the list, and you still only cost one more additional unit of work. And so that means as the size of the list or the size of the problem grows really, really big, the amount of extra work is not going to grow all that big at all. You can see that this curve, we talked about this when we looked at this slide, this isn't a very steep curve. So it's going to take a long, long time for this curve to get any higher on this y-axis. So you're going to take a look at two case studies where you'll explore some actual applications of scalability in computer science. And you'll see in case one how finding an IP address scales well, and how in case study 2, brute forcing a password does not. And we'll talk a little bit more about this after you have a chance to read it. In your reading, hopefully you found out that brute forcing a password scales very poorly compared to the problem of finding an IP address. So let's talk a little bit more about that in depth. So it says here all IPv4 addresses are 32 bits long. Let's just talk a little bit about that before we get too much further. You've probably seen IP addresses before. An IP address might look something like 74.125.224.72. So sorry you have to suffer through my terrible handwriting again, but this is this is actually Google's IP address. Okay, so we said that they're 32 bits long. What that means is that there are 4 sections. All right, here's one, here's another one. They're separated by dots, and the 4 sections are all filled with a number that is going to be something from 0 to 255. Okay, you're not going to see a number bigger than 255 in one of those sections. All right, so what that means is that each one of those numbers is 1 byte. All right, a byte has 8 bits. 8 times 4 is 32. That's where this comes from, saying that IPv4 addresses are 32 bits long. It's because it takes 32 little teeny tiny switches to represent an IP address in your processor. All right, so 32 bits, okay? All right, so hopefully you've memorized Google's IP address by now, but I'm going to erase it. And so the question is, if IP addresses were longer, or if we didn't know exactly how long they were, how would this affect the ability to scale this to a larger and larger number as the size of the IP address gets larger and larger? The question would be kind of the same thing as, what if phone numbers weren't just 3 digits for area code and then 3 digits and then a dash and then 4 digits? So it would be a lot more difficult to find that number, right? And so it really would kind of wreak havoc with our ability to scale these solutions. Now, I will also tell you that those 32-bit IPv4 addresses, we are actually approaching the point where we have used them all up. And so later on in this course, you're going to learn about IPv6 addresses and how they're a little bit different from IPv4 ones, because we actually, in spite of the fact of how large of a number that seems, we have almost used them up. On the other hand, let's discuss brute forcing a password. So we know that passwords don't have a set amount of characters that they can contain. Some people like to keep their passwords short so they're easier to type, but a more secure password is going to have a longer length, but there's no particular right amount of characters for a password. A lot of sites, websites that you sign into will require you to set a password that has a particular minimum length. And why do you think they might do this? They want their website to be secure. So they would imagine that if you had just a little tiny password that was like 3, 4, 5 characters, that someone could probably hack you pretty easily. They could probably guess it. And the longer your password, the less likely it is that they're going to be able to guess it. And so this is how scalability, or the inability to scale well for a particular problem, is actually a benefit for us. And then you can even go so far as to say some require you to have a capital letter or some sort of special character. And this adds to the amount of possibilities that you can have. And in terms of a password, that's a pretty good thing, because it is much more difficult to crack a password that has a big quantity of characters and a big variety of characters.